Welcome to today's webinar. The topic today is most frequently asked questions answered by Dlubal support team. That's the webinar that we present regularly. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the German and English webinars, technical content of the website, customer projects, and so on. I will be the moderator today, and I will also be a presenter. I will present the first part of the webinar. My colleague Stefan Hoffmann, who is the head of customer support, will be the presenter of the second part of the webinar. He prepared the questions. He knows what the customers asked in the last time. Okay, I show you how you can ask questions. At first, I switch off my webcam that you can see the full screen. Just press that button with the question mark, then enter your question in that field, press send, and we will receive your question and we will answer you. Stefan will answer you when I present, and I will answer you when Stefan presents. You can also watch the entire webinar and then email your questions to info@dlubal.com. We turn directly to RFEM, and the first question is, how can I create a calculation diagram? We prepared that simple model, a column base made of surfaces, also a column base plate supported by a surface support, no joints, but we used the material plastic. That's the load combination. We have two load cases, load case 1 for the self-weight, load case 2 for the imposed load, and we combined that with that, or in that load combination. Let's calculate that load combination. You can see here on the right side the convergence diagram, and later we will also create a calculation diagram and the convergence diagram. You see the different load increments. There are 10. And the single iterations in these load increments. So the calculation is done, and you can see on the flanges and also on the column base plate, there are areas where the yield strength is reached, and the material has been plasticized. Okay, then left at the bottom, we switch to the navigator data, and under loads, you can find the calculation diagrams. With a right click, I create a new calculation diagram. In the first step, we use the diagram type 2D basic. Then I select the load combination number 1. Then there are different result types that you can choose for the horizontal axis. I use the increment for that calculation diagram. Then for the vertical axis, I select the surfaces equivalent stresses von Mises. Sigma max. Then the surface number, this flange, and this node. Okay, and you can see the calculation diagram. In the load step or increment 5, where's the yield strength reached, and you can see that the material then plasticide. Okay, so then we copied that calculation diagram. I only select other surfaces or one surface, the flange on that side and this node. And the calculation diagram looks quite similar. So in the next step, we will combine these two calculation diagrams in one diagram. That's why I create a new calculation diagram, left at the bottom. Okay, and I use the diagram type 2D group. The calculation diagram 1, and I select also the calculation diagram 2. And you can see the calculation diagrams are quite similar, but not equal. But you can see they reach the yield strength at the same point. Okay, and we create a forward diagram. This time the convergence diagram. Also for the load combination number 1. Increment, iteration, maximum deformation, Umax. And you can see the single load steps or increments and the iterations. And that's the point where the calculation ended. And you can print all the diagrams directly or in the printout report or to PDF and so on. That's all possible. Okay, that's all for this question and for this model. I switch to the next model. The next question is, can I also optimize parametric cross sections? Yes, that's possible. This is a parametric cross section. We can see that when we turn to the navigator data and I double click on the section, you can see it's a parametric thin-walled cross section. And let's optimize that cross section. First, I have to start, or I have already done the steel design. You can see there's a overloading, and we want to optimize that cross section. So then we turn to input data, then to sections, and we want to optimize the cross section, and we can do that in that field here. Okay, you can optimize according to different parameters: the height, the width, the thickness of the flange or web. In that case, we would like to optimize the width. Maybe because that should be the maximum height, but we can increase the width. So I enter 200 here and maximum 240, and the step should be 10 millimeters. Those are the available cross sections with a width 200 to 240. So let's start the calculation. Okay, and now you can see there's no overloading anymore. 69% is the design ratio, or 0.96. Okay, but what we need to do is to transfer the optimized cross-section to the global model. the moment, we only use the optimized cross-section in the steel design, but not in the global model. But we have to consider the new cross-section in the global model. Yeah, for example, you have a higher self-weight, yeah, and a higher stiffness. Okay, we do a right-click here, then use optimized section in model. Okay, so and we have to run the calculation again. Okay, but design ratio is quite similar, only a small change, but it's still under 1. Okay, so that should be all for this model and this question. I turn to the next model. That's the next model, and the next question is, how do I use the solid type hole? Now you can see where is a bolt to through that section made of concrete. You can see that is the concrete cube. That's the console made of steel, and the bolts. But at the moment there's no hole in the concrete cube. I can show that when I select visibility by selected and related objects. And that's not correct, that you don't have a hole through the concrete cube. How to do that? I show that with the next steps. So I select the 2 bolts, do a right click and then edit, and I use the solid type hole. Okay. Yes, we would like to do Boolean operations. Okay. So, and we have to, those are the new solids. I have to do a right click on the concrete solid and press edit. And then we have to select cancel generated state. Okay. Yes, we would like to do the Boolean operations, and we have to do the same with the console made of steel, edit, and then cancel generated state. Okay. Okay. So, and then I can delete with boundary surfaces the whole solids. Okay. Now there are only 2 solids, but we now have a hole. So let's undo that. Okay, that's the other possibility. I can also select both solids with the solid type hole, then right click, edit, and I select here standard, material steel, and now where are the bolts made of steel? They go through the concrete cube. And the concrete cube has got still a hole. I can show that. You can see the hole. Okay, that's all for these 3 questions. I hand over to Stefan. Stefan, it's your turn.
Thank you, Andreas. I will move on to the next topic. The next question is, how does the DXF import or export work? So I guess most of you are already familiar with it, but I want to deeply explain the new feature. Well, it's not that new, but mainly not explained yet, the DXF2 export. So we offer, as you can see, in the export and import, a direct link to AutoCAD and DXF, let's call it 1 and 2, import and export. And the main purpose of it, or a very deep introduction, can be found in our knowledge base. So there are 3 parts which will deeply explain what is possible, but I will give you a brief introduction into it. So what it's possible to do is that you can of course import nodes, lines and members, and you can as well assign a corresponding cross-section information as well as a material name to it. To do this, you simply have to name the layer corresponding to the cross-section property or material, what we expect. So this is deeper explained as well in the knowledge base. You can as well also import or export surfaces of the 3D surface type, and most likely the main difference between DXF1 and 2 is that the export is similar, but DXF2 offers a deeper or more possibilities with new functionality, and you can directly export also a form-found shape. So you can see a small tent just as a small model where I've run a form-finding process by defining support conditions and inner forces, and we have now the deformed shape of it. And luckily it's now possible to export the deformed shape. So to do this, we simply go to export and now use the direct link to AutoCAD. So the direct link to AutoCAD is most likely the same as a DXF2. DXF2 would only simply create a DXF file, but we run AutoCAD in the background, so we can directly hand over our file and do not need to save it as a file. DXF1 will most likely be gone once DXF2 functions are equally to it. So AutoCAD also uses DXF2 functions. So let's hit AutoCAD. So mainly you are common, of course, that the Z-axis is showing to the top. I usually model to have it showing to the bottom. So first of all, using import or export, you can define points where you want to insert the model. You can also define the axis rotation. So we will of course rotate our structure once, otherwise the structure will be mirrored in AutoCAD. You could also choose what template length you want. You can as well choose more options to export dimensions, FE mesh or FES 3D face. And now mainly the big difference, of course others are in the background, but we can also export the deformed shape as a 3D face. So we hit this button. So now RFEM will communicate with AutoCAD in the background. So it's trying to connect. It will then lock the application for a short time. So it may take some seconds, but as well, depending on the model size, also some minutes. But usually it should be quite fast. Maybe drink some coffee if it's taking too long. And then you should get a message that it was completed. And then we can step into AutoCAD and first of all see nothing. But of course, as you are maybe used to it, we simply have to rotate the cube and then we can see our structure directly in AutoCAD. So you can now continue modeling also with the deformed shape and use your model also in AutoCAD or some other external applications. So now I'm coming to my second question. The second question is, my model is unstable. How can I determine the reason? I guess a lot of customers are already familiar to this message. Maybe you also know how to solve it. We propose a frequently asked question page for it, where it is stated how you can fix some problems. So there can be various reasons for it, maybe some unconnected objects or some hinge chains, or maybe some critical load which is exceeding in the second order theory approach, the stiffness of your system. So I would like to point out some possibilities on where you can evaluate the model in order to check what may be the reason for it. So we have a simple truss girder as an example, and you of course have the opportunity to run all second order theory load cases by using the design situation and showing the results. But most of you, we do not use any design add-on in this file, are hitting the calculate all button, I guess. So also our first order load cases will be calculated separately, and also all load combinations. So what we see is that we get a bunch of warnings in the table. So as well for the dead load case number 1, our stiffness matrix is singular and it points with an arrow at a possible place. So whenever it's a full structural unstable model, then the arrow might not be at the best place, but it's a first intention what may be wrong with our model. So in order to start evaluation, we can simply go into the dead load and assign a structure stability analysis calculation for it. Of course, you would be in the need for this add-on, and we want to evaluate the shape for instability check by mode shape. If we rerun this, of course, the load case will once again result in an unstable model, but the structure stability add-on will show us a shape, what is maybe guiding us towards the reason for the unstable model. As you can see, it's at one of the point where also our arrow was pointing to, and we can see that the members deform quite a lot. So of course you could now stabilize your truss girder, but usually it's only stabilized at the top with some links. And of course I am known to my model, but such a shape may be, if it's also in theory first order, a sign that you have maybe a hinge chain, so too many member hinges, or maybe you're using a wrong member type. And in our case, it's actually the wrong member type, because we have currently only the graphical representation of cross sections colored, but we can change that, of course. And so let's see what we have as member types. And I guess the known user will directly see the reason. We have beams and truss members, and the truss has a hinge at start and at the end. And maybe because we did not pay a lot of attention to it, our upper chord, our down chord was modeled with truss members as well. So we have, of course, 4 members, 4 hinges, so a hinge chain, and we can quickly fix this by assigning, of course, a normal beam to these places. So the beam would be enough because we have done in our diagonal members a member hinge in order to have only normal forces in there. Okay, so we can run the analysis again by hitting calculate all. And now, of course, I know it's stable now. Our load cases theory first order will become stable, but our load combinations will stay unstable, or maybe unstable, it's a bit wrong. It issues that the stiffness matrix is singular. So now the point is it's running first order, and second order it's not running. So this may be an intention that the critical load factor is exceeded. So loads are too high, or the stiffness is too weak for the loads we put on our system, that the deformation and then the additional moments will be too much for our members or our structure. In order to determine this, the quickest move is that you just copy one load combination which is unstable and assign this to a first order analysis, and then we can assign once again the structure stability add-on, but this time we do not use the mode shape without loading because it can be calculated. You can see the CO9 theory first order will be able to be calculated, and we want to check for a critical load problem. So if the critical load factor exceeds 1, the structure is stable. If it is below 1, the force is too high. And if we check for this load combination, we can see that the factor is only 0.66. So this means that our upper chord is too weak for the loads we are putting on it. Of course, it's an example what I created. So the way to fix that would be to mark every member of the upper chord, and then we switch from the weak member to a stronger member, and we can then once again calculate the results again. And now the model should be stable because the calculation theory second order will be successful. We can also check the critical load factor again if we want to evaluate how many times we can maybe increase the load. And we can see that it went from below 0 to most likely 4. And the next problem, what would be in our file, would be just a diagonal member, what tends to buckle. Of course, this is just a way to inspect for unstable models. This assignment does not replace a stability analysis then later on for the steel members. But of course, you need to run the load combinations before you can do the design process later on. All right, we would now step to the last question for today. How do I use the new type of nodes, the nodal links? Maybe you already read about this feature that we introduced, so-called nodal links, and they should be considered that they allow nodes to be coupled to nearby objects, so nodes, members or surfaces, by creating rigid members for you automatically. The rigid members can as well contain member hinges, so it's most likely maybe similar to our rigid link, but not now only for lines, also for nodes. And it is of course planned that we may later on introduce a wizard. So currently it's one type for a node, so we have to choose node by node. You can of course assign it to multiple nodes, but if you are familiar to our type of programming, we will also think about adding a wizard for it. So in the current approach, you can think of adding some members into this opening in order to connect the column. Usually you can do it with a rigid surface. You can also use membrane surfaces, or you use a so-called cross of rigid members. And in order to do that, it's possible to add a so-called link to nearby objects. And this link is then having an object type nodal link, and we can define a nodal link to combine nodes currently to the closest object. Later on it will be extended. You can also define hinges, exclude objects or include related objects, so objects belonging to the line where the node is might be inside. And we would start by adding a search area for 1.1 meters to this node and hit OK. And then we can see that it's of course connecting to one node, which is the nearest one. So this is the node in there. So this is not the type we want to use, so we disable it for this node. We now choose the circular ring in order to select every node of this circle. We split the circle into parts before, and we assign for these nodes the nodal link with 1.1 meter, what we have just chosen. And you can see that you can quickly connect all the nodes to one node without adding a rigid member by yourself, which you have to rotate. So it's quite a smart option to use. A second approach, what might be thought of, is that you can connect nodes 90 degrees to a bent surface. So you do not have to think about drawing a line which will directly cut at the place you want to connect the node. You can simply mark 4 nodes, assign a new link, and we now want to couple it to surfaces. And if we hit now 20 centimeters, nothing will happen because I know it, it's far away than 20 centimeters. So we do, for example, like 2 meters. And if we hit OK, you can see that the nodal links are linking the nodes perpendicular to the surface at the point of the bending. So there's more improvement to be done in future for us. So you can also think about if you have small gaps due to CAD import, you can couple directly them without doing any other stuff, maybe if the wizard is introduced. So keep on track. Thank you for your attention, and I will now hand back to Andreas.
Thank you, Stefan, for your presentation. I have an additional hint. You can book our online courses. For example, for RFEM 6, that's the course for beginners. Then the Eurocode 2 course for the reinforced concrete design. Eurocode 3, the steel design with RFEM 6. Then on the next slide, you can see the Eurocode 5 course for timber design and also course packages. Just scan the QR codes in the middle, or you can click on the links at the bottom for the prices and more information. An additional hint, you can get the single courses for free when you send us a customer project, and when it is published, you can get as a gift such a single course. Also, that means RFEM 6, Eurocode 2, Eurocode 3, or Eurocode 5. Just write me an email to info@dlubal.com, and I will answer you and write you what I need for materials. There's no much work for you, but you can do advertising for your company, for your project, and additionally, you will get such a free course. Okay, that should be also all from my side. I thank you for your attention. Thanks to Stefan for the preparation and for your part of the presentation. I wish all a nice rest of the day. Bye-bye.